Alright, so got a couple of more questions. So I wanted to answer these, and if you've got any other questions, let me know. If they're easy, I'll uh, answer them through email. But some people, I'm not going to mention any names, send me huge, long, extended questions about 17 different problems at the same time. Just kidding. No, if you've got questions, I want you to ask them. So make sure that you do so that you understand what's going on. This is the first one that we're going to look at. It's on 2-2, and this is number 12 on the assignment. It says graph the functions in behavior model. So what you're going to do here, let me get my writing utensil program up. So what you're going to do here, the in behavior model is all you're doing, it's the same thing as thinking about this as the limit when x approaches infinity or negative infinity. That's all you're really doing. So you can do things that are similar to when you're doing that limit. And what you want to do is, as you get an in behavior model and go off way over here to the positive x direction, x's are getting larger and larger and larger. The only thing that's going to matter is that x to the fifth right there. The rest of these are going to be as you know, not when x is 10, not when x is 100, not even when x is 1,000,000. We're talking when x has so many zeros, you know, it would take you forever to write all the zeros down behind that 1. That's the kind of numbers we're talking about when we say going to infinity. And this 3x to the fifth is still going to be way more than an x to the fourth. Even though there's only 1 degree separating them there, this number is going to be so many more times larger that it's going to control the value of that top. So the rest of this we can kind of ignore, because that's going to have a negligible effect as x gets humongous. And on the bottom, the same thing is similar. The 2 is going to be 2 is going to be 2 no matter what x is. As x gets larger and larger and larger, though, this thing right here is going to control all the value. So that is what we end up with. And we can ignore the 2, we can ignore all this stuff here, so we end up with 3x to the fifth over x squared, which is going to simplify to 3x to the third. So that's what your in behavior model is going to behave like. So your in behavior model is going to be 3x cubed. So what does an x cubed look like? Well, if you're throwing in negative numbers here, what do you know? You know that you're going to have a negative number come out. So that means it's going to be this one right here. Hold on, let me check one thing. Okay, now here's the thing. This may also be a problem too. If this had been 2 minus x squared, the 2 is still negligible, but that x squared is still a negative. So if you did this simplification here, you would now have a negative out here, and then that would make it this graph, not that graph. So be careful about having a minus in there. Just because you're getting rid of a lot of stuff, don't lose the sign of the term that you're keeping. It is important. So you have to keep that sign if it's going to make a difference. You have to keep the sign anyway, but make sure you keep the sign, especially if it's going to make a difference. So the answer for this question as it is D. If that had been 2 minus x squared, it would have been C. All right, next one we're going to look at is 15. Use the graph of that thing. This is the problem that I told you guys. I don't want you to think about this in the way that they're showing you. This is the one that's, the way they show you to do it, thinking it this way, is more complicated than just writing out and simplifying this thing. So if we're going to take the value, as the limit as x approaches negative infinity of this thing, we're going to go ahead and move that to the bottom. So we've got 3x over e to the negative 2x. Now the thing is, oops, sorry, that's not a negative anymore. That's a 2x. Now, here's another way that you can do this. If we do the limit as x approaches negative infinity of this, you can also do this little trick of taking the negative, go ahead and put it in all your x's up here, and then take the limit as x approaches infinity. That trick works also. So if I want to do x approaching infinity, I've got to go ahead and go in and put a negative everywhere I have an x. So I have 3 times negative x over e to the 2 times negative x. So now, where we moved it to the bottom before because we had a negative in our problem, it's a negative again, so we're going to end up moving it back up. So when we multiply the 3 times the negative x, we're going to get the limit as x approaches infinity of negative 3x, that came from this part, multiplying it out, and then this, we end up with e to the negative 2x again. Remember, a negative exponent simply means we want to move it from the bottom to the top or the top to the bottom. In this case, since it's on the bottom, we got to move it back up to the top. So we end up with e to the positive 2x. All right, now as x goes to infinity, what's going to happen here? Well, we've got negative infinity right here, and this is going to go to infinity also, so we're going to end up with negative infinity. Now, if this had been approaching positive infinity, let's say that had been not there, or it's, let's say, just say it's a plus, then we don't have to do this part right here. And right here, so ignore the rest of this. But if we had had x approaching infinity, now we can put infinity in right here, and we're going to get 3 times infinity over e to the 2 times infinity. And that's where you've got to think about what's growing faster. And e is always going to grow faster than a linear expression. Think about your graphs as you're going off to positive infinity, which one's going up faster. And it's definitely going to be the thing on bottom. So if the bottom is growing way faster than the top, then that's going to approach 0. So that's where approaching negative infinity gives us a negative infinity, but approaching positive infinity, we go to 0. So it's very, very important. Can't emphasize this enough. You've got to make sure that you're paying attention to what that x value is approaching, because it makes a huge, huge difference in the limits. All right, so I went over and I skipped over this one when I did the video earlier, because you guys need to know what your unit circle values are. So in this case right here, this is from 2.4 again, rates of change in tangent lines, and this is number 3. Well, the average rate of change is still going to be y2 minus y1 over x2 minus x1, or also, remember it's nothing more than the slope, it can be, in this case we're dealing with h, so h of pi over 4, nope, sorry, pi over 3, minus h of pi over 4, all over pi over 3 minus pi over 4. So that's where you've got to know these values right here. And remember, all that's doing, you're just doing the sine. So we've got the sine of pi over 4 minus the sine of pi over 3 over pi over 3. Oh, sorry, I got those backwards again, didn't I? Pi over 3 minus pi over 4. And then pi over 3 minus pi over 4. All right, so the sine of pi over 3 is going to be the square root of 3 over 2. The sine of pi over 4 is going to be the square root of 2 over 2. And on the bottom, pi over 3 and pi over 4, we're going to have to get a common denominator, which is going to be pi over 12. So we get 4 pi over 12 minus 3 pi over 12. So we got a common denominator here, so we've got the square root of 3 minus the square root of 2 all over 2 divided by pi over 12. Alright, so I'm going to have to move out here. So we've got the square root of 3 minus the square root of 2 over 2 divided by pi over 12. Well, remember, dividing by a fraction is the same thing as keep, change, flip. So we've got the square root of 3 minus the square root of 2 over 2 times the reciprocal of this, which is going to be 12 over pi. So at that point, all we have to do is cancel. So we got that, and that's going to be 6. So we end up with 6 times the square root of 3 minus the square root of 2 all over pi. Then when we distribute that through, that's going to be one of these answers over here. So 6 square roots of 3 minus 6 square roots of 2 over pi minus, so it's going to be D. All right, next one we want to look at is number 4. And yeah, I'm not working all this out. I'm not doing all this for you guys. Here's the thing. All you're doing is you're using these points. If we're looking for PQ, the slopes of the secants for PQ. So I've got PQ1. So I've got this point right here and that point right there. So there are my 2 points. So if I want to find the slope, remember all it is y2, 650, minus y1, 139, over x1, or x2 minus x1, 20 minus 7.1. And then you just calculate that. So 650 minus 139 is 511, and 20 minus 7.1 will be 12.9. And that's going to give you 39.6. Round to the nearest integer is needed, so it'd be 40. So all you're doing is using the slope. And you're doing that for all those. All right, so that's all the questions that were answered that was asked specifically. There's some others that I've got to look at. But yeah, hopefully that helps a little bit.